Our last video left off at Part B, Question 3. What is the walking rate for each student per minute and per hour? If we look at Elena's data, she walks 1 meter per 1 second. We multiply this by 60 seconds in 1 minute, and that comes out to be 60 meters in 1 minute that Elena can walk. We can then use that data, 60 meters, in 1 minute to find out how far she can walk in 1 hour. Multiply that by 60 minutes in 1 hour, and that comes out to be 3,600 meters per hour. Gilberto can walk 2 meters in 1 second. To find out his walking rate per minute, we simply again multiply by 60 seconds in 1 minute, and that comes out to be 120 meters per minute. We take that data, 120 meters per minute, and multiply that by 60 minutes in 1 hour, and we find out that Gilberto can walk 7,200 meters in 1 hour. Leanne can walk 2.5 meters per second. We multiply that by 60 seconds in 1 minute, and we get 150 meters per minute. Take that data, 150 meters per minute, multiply that by 60 minutes in 1 hour, and we find out that Leanne can walk 9,000 meters per hour. The final question asks us to look at the following charts and equations and determine which show a linear relationship. If we start with looking at George's data, we can see that his time each time is increasing by 1 second. However, the distance in which he is traveling per second is changing. From 0 to 1 second, he's walking 2 meters. From 1 to 2 seconds, he's walking 7 meters. From 2 to 3 seconds, he's again walking 2 meters. From 3 to 4 seconds, he's walking 9 meters, and from 4 to 5 seconds, he's walking 5 meters. Because the number of meters is changing from second to second, we can determine that this is not going to be a linear relationship. Looking at Elizabeth's data, her time goes up by 2 seconds every time, and her distance between every 2 seconds goes up by 3 meters. Because her distance increases by the same amount every 2 seconds, we know that this will in fact be a linear relationship. The equation listed for Billy's walking rate will also be a linear relationship because we can see that Billy will walk 2.25 meters every second. And as the seconds increase, the distance will increase by 2.25 meters per second, equating to a linear relationship. If we look at the equation that represents Bob's walking rate, we can see that it says time equals 100 divided by his walking rate. Because the time is dependent on the walking rate, we know that that rate is not going to stay the same, and this will not lead to a linear relationship. Moving on to the next page, question 1 says that Hoshi walks 10 meters in 3 seconds. What is her walking rate? We can simply solve that by taking 10 meters, dividing it by 3 seconds, to get an answer of 3.3 meters per second. To solve for how long it will take her to walk 100 meters, we take the 100 meters, divide it by 3.3 meters per second, and we get an answer of 30.3 seconds. To find out how far Hoshi is going to walk in 50 seconds, we take her rate of 3.3 meters per second, multiply that by 50 seconds, and find out that she will walk 165 meters in that 50 seconds. To write an equation, we do similarly to what we have done in the previous 2 pages, and we find that D equals Hoshi's walking rate of 3.3 meters per second times T, or the number of seconds that she would be walking. Question 2 says that Milo is walking 40 meters in 15 seconds and Mira walked 30 meters in 10 seconds. Who is walking faster? To figure out the answer, we need to find each of their walking rates. So we can take 40 divided by 15 and find out that Milo is walking at a rate of 2.66 meters per second. Mira is walking 30 meters in 10 seconds. Divide those numbers and we find out that Mira is walking 3 meters per second. Therefore, Mira is walking faster. For question 3, we are going to use the data table that is provided. A is asking us to find the average rate at which each person travels during the first 3 hours. To determine that, we can take one of the miles and the corresponding hours and divide those 2 things to find out their average miles per hour. For Jose, that would mean doing 15 divided by 3 to find out that he is riding at about 5 miles per hour. For Mario, we can take the 21 and divide that by 3 and find out that Mario is riding at about 7 miles per hour. Finally, for Melanie, we can take her 27 and divide that by 3 to find out that she is riding at 9 miles per hour. To find the distance that each person would travel in 7 hours, we take their miles per hour. For Jose, that is 5. Multiply that by 7 hours and find out that Jose will ride 35 miles in 7 hours. For Mario, we take his 7 miles per hour, multiply that by the 7 hours, find out that he will ride 49 miles. For Melanie, we take her 9 miles per hour, multiply that by 7 hours, and find out that she will ride 63 miles in 7 hours. Part C asks you to graph the time and distance for all 3 riders on the same coordinate axis. You can see that I have done that here. I have placed time on the bottom of my graph, distance along the y-axis. I gave each rider their own color so we can determine whose data is which line. Part D asks us to find the distance each person travels in 6.5 hours using this graph. To do that, I need to find 6.5 hours on my graph. For me, that's about here. And then I follow this line to each rider. For Jose, that would be here, a little further left. For Mario, that would be here, again, a little further left, harder to do on the iPad. And for Melanie, that would be here, again, a little further left, a little harder to do on an iPad. I then follow this spot over to the miles. For Jose, this would be a roughly 32.5, 33 miles if I follow this line over here. For Mario, it would be about 45 miles. And for Melanie, it would be about 59 miles. Question E asks you to use the graph to find the time it would take each person to travel 70 miles. I had to do this on my own paper graph because, as you can see on here, this graph only goes up to 62 miles. So I had to add on graphs paper to get up to a certain number of hours and reach up to 70 miles. All I did once I had added graph paper was extend each of these lines until they hit my 70-mile mark. For Jose, that meant that it would take him about 13 1/3 hour to ride 70 miles. For Mario, it would have taken him roughly 10 hours, as I took this line, followed it down to my hours axis, and it lined up with the 10. For Jose, it would take him about 8 1/4 hours, as I took this line, traced it down to the hours, and it lined up with about 8 1/4. On the fourth and final page, questions F through I are referring back to that data table with Jose, Mario, and Melanie. F is saying, how does the rate of each person's ride affect each graph? We had determined previously that Jose's rate was about 5 miles per hour, Mario's rate was 7 miles per hour, and Melanie's rate was 9 miles per hour. As you can tell by the graph, as the rate increases, the steepness of the slope of the line also increases. So this is Jose's line. We can see that his line is not nearly as steep as Melanie's line, whose rate was 4 miles per hour faster than Jose's. Question G is asking us to write an equation to calculate the distance traveled after so many hours for each rider. For Jose, we had determined that his rate was 5 miles per hour, so Jose would simply be D equals 5 times T, meaning for every hour given, Jose will ride 5 miles. For Mario, we determined his rate was 7, so his equation would be D equals 7 times T. Melanie, we determined its rate was 9 miles per hour, so her equation would read D equals 9 times T. Part H wants us to use these equations that we just found to determine how far the person will travel in 6.5 hours. For Jose, that means D equals 5 times T. We know that T equals 6.5, so we substitute that in, and we get D equals 5 times 6.5. Solve that out, and we get 32.5 miles. For Mario, his equation is D equals 7T. Substitute 6.5 in for T. And we get distance equals 45.5 miles. Finally, for Melanie, her equation is D equals 9 times T. Substitute 6.5 in for T. And we get that Melanie will ride 58.5 miles in 6.5 hours. Question I asks, how does a person's biking rate show up in his or her equation? And we can see that for each rider, their rate shows up here, meaning that their rate multiplied by time showcases the distance in which they would travel in that amount of time.